This lecture is going to talk about metabolism and enzymes. Metabolism is talking about the reactions that go on in your body, such as digestion reactions, meaning digestion of food for the release of energy. So chemical reactions of life, forming bonds between molecules. We do this by dehydration synthesis. Remember, dehydration means to remove water, synthesize means to make, so to join things together by removing water. And we refer to these types of building reactions as anabolic reactions. Breaking bonds between molecules is the other type of reaction that takes place in living organisms. We call these hydrolysis reactions. Remember, hydro meaning water, lysis meaning to split. So we actually break molecules apart by replacing the water that we took out in the first place. So to split using water. These are known as digestion reactions, and they're also called catabolic reactions. So if you think of the word catastrophe, in a catastrophe, things fall apart. So catabolic reactions, we have molecules that are, quote, falling apart. So example of dehydration synthesis, we've covered this before. Again, we have two monomers here, monomer of glucose, remove the OH from one, the H from the other to form water. And this is conducted by a helper molecule called an enzyme. We also have enzymes that can do the opposite, putting the water back into our bond, and by adding this water, we can break our monomers apart. So, chemical reactions and energy. Some chemical reactions release energy, and we call these exergonic. The prefix exer means out of or to release. So whenever you digest a polymer, by the way, this is why we digest our food, we break it down to release energy or to have a net release of energy. And we do this with hydrolysis reactions, also known as catabolism. Again, catabolic, catastrophe, falling apart. Some chemical reactions require an input of energy. These are called endergonic. So the opposite of exer is ender, meaning into, so putting energy in. And these are how we build polymers. So when we build a polymer, it requires an input, a net input of energy. So dehydration synthesis, adding that water back to join the monomers together, is an endergonic reaction. And we refer to this as anabolism, or an anabolic reaction. So we can represent these types of reactions using what we call the energy hills, or graphs. So when we look at this graph here, what it's showing is on the x-axis the progress of the reaction, and on the y-axis the amount of energy, or the change in energy. So here we have reactants, here we have the products, and what we're seeing is the amount of relative energy stored in the reactant and the amount of energy that's in the product. So as we go along the progression of this reaction, we see that we have an input of energy, then we get that energy back out, and then we get a little bit more energy out. So this energy hill cancels. So the energy that was inputted here is canceled out by the energy that comes out here. The net energy, meaning the energy that's going to be left over after we inputted in the beginning, is the net release of energy. So this reaction, would that be endergonic or exergonic? We released energy. Here's a Dora the Explorer moment. That is going to be exergonic. Energy is released. So in this reaction, energy, we have a net release of energy. We did have to put an initial input of energy. We got that energy back, and then we got a little more energy beyond that, net release. So this is exergonic. These are going to be digestion reactions, also known as catabolic reactions. So that's the net energy release. And we refer to this as free energy, the net change in energy of the system. And so when we release, that's going to be negative, a loss of energy from the system, being released. So negative meaning losing from the system. Delta G, this stands for Gibbs free energy. If you take AP chemistry, we'll talk a lot about Gibbs. What you just need to know is that delta G is referring to the amount of energy that's either inputted to the system or released from the system. When we release energy from the system, that is a negative change. That's what delta means, is change in free energy. So the opposite here, if you take a look, we're putting energy in, putting more energy in, okay? So if we have actually a net increase of energy being put into these molecules. So this is going to be an endergonic reaction because energy was invested, and this would be a synthesis type reaction. I haven't found a better image for this. If you look, we have molecules together and they're spreading apart. That would not be an endergonic reaction. These should actually be the opposite. Separate molecules here being put together into a larger molecule. But what you can see is we had a net input of energy. So what do you think the delta G is going to be? Positive or negative? Positive. So we're going to have a positive change, meaning that the system gained or we added energy into the system. So we have a net gain of energy in the system. So this free energy is the amount of energy that's available to do work. So in this system, we're releasing energy that can be used to do work in another system or for another reaction. Here, we actually had to input energy to make the reaction occur. So we can use this to our advantage. We can actually pair up exergonic and endergonic reactions together. So to do the reactions of life, what we do is something called energy coupling. We couple an exergonic reaction, one that's releasing energy, with an endergonic reaction, one that requires energy. So here we have a polymer, well, really a dimer, and we're going to break it apart into its separate monomers. When we break that bond, we get a net release of energy. So this is a digestion reaction. We get a net release, nice explosion there to represent our energy. And then that energy can be used to power a synthesis reaction. So to build something requires an input of energy, and we get that energy from breaking apart something else. This is why you eat food. When you eat your food and break your food and digest it down, you get a net release of energy, and then that energy can drive the synthesis reactions of your body, things like making proteins, making new cells, copying DNA. So the energy from this digestion, this exergonic reaction, can be used to power our synthesis reaction. So we're going to take these two monomers and we're going to put them together by dehydration synthesis to make a larger molecule. So fueling the body's economy. So we eat high energy organic molecules, things like carbs, lipids, and proteins, and that's our food. We break them down, so we digest them, and that would be an exergonic reaction, catabolism. And we capture that released energy in the cells to use that energy to build other things. So build more cells, to copy DNA, to make proteins, etc. So the need for energy currency. So how do we transfer this energy from one reaction to another? And we talked about this with nucleic acids. We have a molecule that we use in our body that acts as an energy currency. It's how we actually exchange energy or move energy from one reaction to another. And that molecule is something called ATP, adenosine triphosphate, which is a nucleotide with 3 phosphate groups. So ATP, adenosine triphosphate, that's how it's pronounced. And here's the molecule here. Now the reason why it's called a triphosphate, I bet you can guess, is that there's 1, 2, 3 phosphate groups. Triphosphate. And here's the rest of the molecule. The adenosine comes from the fact that we have a nitrogen group called adenine. That's the A part. And here's our 5-carbon sugar. This is what makes it a nucleotide. So here are 3 parts of our nucleotide. It's a special nucleotide in that it has 3 phosphates instead of 1. So modified nucleotide. So 1 phosphate would actually make it AMP, adenosine monophosphate. We can add another phosphate to it and it becomes ADP, adenosine diphosphate. And then to get to triphosphate, we add that 3rd phosphate group and we get ATP, adenosine triphosphate. And with each phosphate that we add, we're storing more energy in the molecule because if we remember, phosphate has a negative charge. So you add a phosphate group, another phosphate group, and negative, they repel each other. So that's going to create a relatively unstable bond. Then you try and force and cram on a third negative group, and that makes the bond even more unstable. So we have what we call high energy bonds. So adding a series of phosphates, that's actually endergonic because we're building, right? We're adding on these phosphates. So it takes an input of energy to build this ATP. And that energy is going to come from the digestion of your food. Later in the year, when we talk about cellular respiration, we'll talk about how we get that energy out of food and transfer it to ATP. But for right now, think of ATP as our energy shuttle in our body. And anytime a chemical reaction occurs, we're going to have some ATP exchanging hands. That's why we call it the energy currency of the body. So there are high energy bonds. So again, how does ATP store that energy? Starting out as a molecule of AMP, adenosine monophosphate. We cram on one phosphate group, and we have a little bit of stored energy in there, and we are ADP. Now ADP, adenosine diphosphate, we can add a third phosphate to it, and now we have ATP. So each negative phosphate is more difficult to add, and therefore more energy required to add it, but also more energy that is stored in that bond. So bonding the negative phosphate groups together is unstable, and so think of these as spring-loaded, thus the sound effect. So the phosphate groups will take any excuse necessary to pop off, and so to lose the third phosphate group actually is a very exergonic thing. So when we break off this third phosphate, we get a net release of energy, and we use that net release of energy to run synthesis reactions. If this is a little confusing, we'll learn about it in more detail again when we get to cellular respiration. Okay. So ATP, how does it transfer energy? Transfers energy by going from being ATP back to ADP. And when we remove that third phosphate, that is an exergonic reaction. That is a digestion, and we're breaking it down, and we're releasing energy. It's exergonic. So we get a release of energy, and in fact, we get a release of energy of 7.3, I believe, kilocalories per joule, or per mole, sorry. And we use this net release of energy, this negative 7.3 kilocalories per mole, to fuel other reactions. And we call this process phosphorylation. And I bet you can guess why we call it phosphorylation, because what we're doing is we're adding, or lation is talking about process of, it's the process of transferring a phosphate group. And what it does by adding this phosphate group to other molecules is it also destabilizes those molecules. And to do this, to transfer the phosphate group, we use an enzyme called a kinase. You don't have to worry about memorizing it, but if you should ever see kinase, you should think that that's an enzyme that transfers phosphate. So building polymers from monomers, we use the help of ATP. So this is a synthesis reaction. So if it's synthesis, is it endergonic or exergonic? It's an endergonic reaction. It's a building reaction. So where do we get that energy to join these two molecules together? We get this by pairing it with a reaction that is exergonic. So to do this, it requires an input of 4.2 kilocalories per mole. That's a unit of energy. So where do we get that energy to build the molecules? So we need to destabilize the monomers. We need to pair it up with an exergonic reaction. And we do that by phosphorylating. So here's our ATP, and what we're going to do is we're going to transfer a phosphate group from the ATP to this monomer. And if we do that, that is an exergonic reaction. We get a net release of negative 7.3 kilocalories per mole. So pairing this reaction up here with this exergonic reaction here, the net reaction becomes exergonic, and we can make the reaction go forward.